How to use the Stitching Calibrator for video 360 calibration. Hi everyone! In this tutorial, you will learn how to calibrate the 360 projection and stitching parameters for fisheye video footage in RidgeRun Stitcher Calibrator. If you're planning to use the RidgeRun Stitcher alongside the RidgeRun Projector to generate 360 videos from fisheye cameras, this is the right video for you, so stick around. The first footage we're going to stitch is from a 3-camera array. The cameras are separated by an angle of 120 degrees. Each lens records 180 degrees vertical view. However, due to the sensor capture configuration, part of the top and bottom view is cropped out. The sensor 0 is looking to the left side of the car, the sensor 1 is looking to the front, and the sensor 2 looking to the back of the car. Okay, let's get started. The first thing we need to do is to prepare the directory with the sample images to calibrate. Following the calibrator requires structure. We need a project directory with a sample folder for each one of the cameras. That should always be numbered from 0 to a number of images to stitch -1. Each folder contains the corresponding sample images. Now, open the Stitcher Calibrator and click on 360 Calibration. This will open the 360 Calibration workspace. Load the prepared samples by going to File, Open. This opens a dialog box. Navigate to find the project directory 360 and click Open. This will load the samples for each camera in the camera's window. The first image is highlighted in the light blue rectangle. The preview window shows the quadrectangular 360 projection of this camera, and the stitching window shows the 360 image of the 3 cameras. To start the calibration, we need to define the lens aperture using the lens control here. This footage was captured with a 180-degree lens, so just keep the default value. Then, we need to define the lens area. With the help of this green circle overlaid over the image, the radius control here, and the circle center controls below. The circumference of the lens was preprocessed, so the position of the green circle is really close to the actual edge of the lens, but it needs some refinement. Anything outside the circle will be masked out, and the diameter of this circle will correspond to the lens aperture, 180 degrees in this case. So a close selection of the circle to the lens border will allow better projection and matching the 360 projection. If you choose a smaller circle, you will need to adjust the aperture as well, because you are reducing the angle of vision. Let's adjust the circumference for each of the cameras starting with sensor 0. First, adjust the window and zoom in for a better view, and start adjusting the radius here. Any of the controls in this panel can be changed in 3 different ways. Using the mouse, clicking the box arrows up and down, like this. Using the keyboard arrows up and down like this. Or writing the value we want directly in the box. Okay, now that you know how to change the controls, let's adjust the lens circumferences close to the border. Restart the value to 780. There you will see a black border corresponding to the left side of the lens mount. Let's move the circumference to the right by moving the center X up. Okay, that looks good. And reduce the radius a bit. Let's try to use the same radius for the next camera, 778. In plain sight, that looks good. However, in the preview window, we can see a small black border down here at the right side. So let's try to move it to the left. Okay, it looks pretty good now. And finally, let's use the same radius for the last camera, 778. It looks pretty good. Let's keep it. We can run with this configuration. In a perfect scenario, this will be enough to stitch together our images. But looking at the stitch results, this is barely the case. Look how the cars are misaligned. And here, the sidewalk is also misaligned, even though the car rear mirror seems to be better aligned. There are several factors that can sum up to the imperfect result. One of them is the camera setup misalignment, which means having the lenses at a different horizontal, vertical, or optical axis. The rotation controls here provide a mechanism to correct the fisheye camera lens system. When changing these controls, you can imagine that you're rotating the camera itself. The controls can change between minus 180 and 180 degrees. Note that the x-axis is assumed to be at the right side of the camera, so x-rotation can be used to correct the fisheye tilt angle. A positive value will tilt down the camera, while a negative value will tilt it up. The fisheye camera is assumed to be looking over the y-axis, so the y rotation is used to roll the fisheye. A positive value will rotate the fisheye image counterclockwise, while a negative value will rotate it in a clockwise direction. And finally, the z-axis is assumed to be of the camera, so z rotation is used to pan the fisheye around the 360 horizon. The z-angle is initialized to have the camera fisheye distributed along the 360, in this case a 100 difference between the cameras. Another factor is the parallax error. In a perfect scenario, all the cameras will have the same nodal point render to an extended view of a scenario. However, it is physically impossible for cameras to occupy the same physical location, causing a different point of view of the same objects. The different position between the cameras will render a different relative position of the objects in the capture image of the scene. At stitching, we can try to align the objects at a certain depth, but not all the depths at once. In this example you can see here, the car rear mirror is mostly aligned, but the cars in the background are misaligned. We're going to try to align the center of the image, and you will notice how the stuff closer to the car might end up as well aligned. So this is something you need to decide in which depth you are interested in, and focus on stitching that area. The selection totally depends on your scenario and use case. We're going to move the center image to align it to the image with the left car view. Let's select the center image corresponding to sensor 1 in the camera's window. You can confirm here in the preview window that we have the right image. Now you can inspect the center image stitching by clicking on it. If you hold the click, you will enable transparency for this image. By clicking and releasing, you'll notice that we need to move this car a little bit to the left and up. So let's start adjusting the controls. Enable the transparency checkbox down here to make everything transparent and better see the alignment of the cars. Start with the Z rotation to move the car to the left. Okay, that looks better. Now use the X rotation to move it a little bit up. And there, the cars and sidewalk alignment is better. It is not perfect just yet, but good enough for this example. As expected, the rear mirror misaligned further because of the parallax error. Before continuing with the adjustment, let's check the controls down in the control panel. The lock control, when checked, will disable the movement of the images in the stitching window. You can click and try to drag them, but they will not move. When you remove the check from the lock, you can actually move the images by dragging them. You can click on the reset button to restore the positions of the 360 images. Also, you can select all the images like this and click and drag them to move them in group. This can be helpful to use the overlay grid to align certain object. Okay, let's enable the lock to avoid moving any of the images by accident when toggling an image transparency by clicking. Remember that you can enable transparency on the whole stitching, but I prefer the individual transparency to focus at specific areas. You can continue using the controls to align the images until you're satisfied with the result. For this example, we're going to leave it like this. So let's save the parameters. Go to File and Save. Navigate to the directory we want to save the file and click Save. This is the resultant JSON file with the parameters for the RidgeRun Projector and CUDA Stitcher. It contains a projection array used to configure the RidgeRun Projector and the homographies array used to configure the CUDA Stitcher. On one hand, the projections array contains an object per camera with the projector configuration parameters. The name of each parameter field corresponds to a projector property. On the other hand, the homographies array contains the image's information and corresponding homographies for each pair of images to stitch. Now, let's perform a calibration from start to finish of a more common camera array. This array consists of two cameras back to back with fisheye lenses of 195 degrees of field of view. First, open the Stitching Calibrator, select 360 calibration and open the project sample by going to the File menu and selecting Open. We have this directory prepared with a folder for each of the images, named 0 and 1 as expected, and each folder contains a sample image of the corresponding camera. By default, the tool sets the camera aperture to 180 degrees. By now we have cameras of 195, so let's change the lens parameters for each of the cameras. Now adjust the circumference starting with the camera 0. The initial green circle is out of the border, so reduce the radius. Let's try 700. Oops, it was a little too much. Anyway, the circle looks out of center, so let's move the circle down by moving the y coordinate center. Remember, the image vertical axis starts in the top left corner and positive values go down. The circle is better centered now. Continue increasing the radius by keeping a bit of the border to have a small range to better adjust the center and aperture when stitching. Moving forward to the next camera, set the same radius and adjust the center. Again, we need to change up the Y center to move the circle down. And adjust the X center as well, moving it to the left. Alright, seems to be ready now. Now let's see the stitching result. I like to keep visible the camera's window and the stitching window to keep moving between the cameras while adjusting the controls. Again, you can click and drag to move the images. However, we recommend to keep them aligned and just use the controls to move and align the projections. Click Reset to restore the position, adjust the position to center the stitching, and select Lock to avoid any unwanted movement. So now, let's focus on the overlap regions. Zoom in the region on the left. Toggling the transparency, it becomes visible that this yellow circle is misaligned. Zooming out with the transparency enabled, you can clearly see the overlap regions. Let's zoom in to the overlap region on the right. See how this tree looks duplicated. Notice how by clicking one image makes it to be on top. Toggling the top image, you can see clearly the tree movement. Zoom out to see the big picture and disable the transparency to see how the objects move when we select the projections of camera 0 or camera 1. Clearly the objects are moved. So we first are going to try to adjust the Z position. Move it a little bit on each of the cameras to split the difference between them. Besides changing Z to translate the images horizontally, you can use the center X control as well. Just bear in mind that you will have a smaller range of movement. Also, you can notice how the yellow wheel has a vertical disparity, so we're going to try to adjust the image to try to match them. There, they seem to be at the same vertical position, but the images are not horizontally aligned. Since we leave the green circle smaller than the visible lens circumference, the aperture is not a perfect 195 degrees. So we can use the lens control to adjust the horizontal alignment. Notice how decreasing the aperture, the images are getting closer. However, it is recommended to change it equally for both of the cameras to avoid big distortion. Let's select the other sensor and decrease the lens control there as well. Look how with 190 degrees, the trees are now closer, but still need to reduce it a little bit more. So let's go back to sensor 1 and decrease the aperture. And let's do the same for sensor 0. There it looks pretty good. If we zoom in the tree, you can see more clearly that it is fairly aligned. Let's enable transparency and see if we can make it look better. Oh no, reducing the aperture makes the tree move away, so let's go back to 187. Okay, let's check the other overlap. It looks great. Toggling the focus of the image, we can see how the difference is minimal. Notice how this region of the box is not aligned, but it is really close to the camera, so it is expected because of the parallax error. Since we're interested in the further object, we're not going to pay any attention to the box. Alright, we're done. Let's save our results. Go to File, Save, write the file name 360JSON, and click Save. You can use the parameters in this file to configure the RidgeRun Projector, and use the JSON as it is with the RidgeRun CUDA Stitcher to get a file like this one. Great! Now you know how to use RidgeRun Stitcher Calibrator to calibrate a 360 camera setup using sample images. So all there is left to do is for you to go and have fun with your own project. Please remember not to hesitate to contact us if you have any questions about the tool. We are eager to help.